Okay, hello everyone. We're doing physics for today. And remember that last time from physics we were talking about what energy was. So this time we're going to be focusing on one particular aspect of energy, which is electricity. So we're going to be dealing all with the basics of electrical circuits and how electrical circuits even work in the first place, what are the principles of them, and hopefully once you've learned about this, you have a better idea of how circuits around us even work in the first place, because we use circuits all over the place. In fact, if you're watching this right now, you'd be relying on circuits that's showing you this information because the circuits are making up your phones and your computers and so on, right? And even if you're relating it towards biology as well, we are relying on neuronal impulses, which is basically another type of circuit because it's transferring charge. That's how nerves actually work. And then towards chemistry, this will link with another topic in chemistry that's called electrolysis. So this is used all over the place either way. Okay. All right. So electricity on its own is very interesting as a topic, I think. But let's just go through what the word itself actually means, right? Now, in normal English, if someone is talking about electricity, they are usually talking about whether their home is receiving electricity or not, right? Electricity as a word is to do with the transfer of electrical energy, okay? So that's what electricity can be defined as. It is basically the transfer of electrical energy. Okay, that's one kind of way of looking at what electricity means. Now, the tricky thing about electricity is that in order for electrical energy to be transferred, it always has to be done so in a closed loop. So let me give you an example of this. I could have a typical kind of loop here where I could have the battery of a cell, where this end here is positive, and then I could have this end of the cell here, which is negative. So I could hook this on with some wires, like some copper wires. Now remember from chemistry, these copper wires are metals, and the reason why they can transfer electrical energy through them is because of the metallic bonding that's in them. So you've got this kind of wire here, the current pops out of the positive end, and then it flows into this bulb over here. Right? Once it flows into the bulb, we have energy that's being transferred from a chemical store, which is chemical energy inside here. We have electrical energy through these wires. And then we finally have this electrical energy that's being converted into light energy as well as heat energy. Okay, from this kind of filament bulb here. Right, so that's the typical process of what's going on. Now, as I was saying in the beginning, electricity can really only exist as a loop. Okay, because if you've got a battery source that's providing energy to the circuit, you need one end that's positive that flows towards the negative end. Okay, another kind of small point as well is this positive end over here that is producing a current. Some of you might notice that the only things that carry a positive charge are the protons, and the electrons carry a negative charge. So it's a lot more difficult for the protons to actually be flowing. It turns out in reality the protons don't actually flow. It turns out in reality it's actually the electrons that flow this way. However, in physics we define current to be the movement of positive charge. That is to say, the movement of electrons flowing this way towards the left, like this, is equivalent to the movement of the protons that are, or I guess you could say positive charge that's moving like this instead. Okay, so just be mindful that in physics, when we're talking about current, which is the movement of a charge, right, we are talking about positive charge, not negative charge. Okay, so we're not talking about the actual flow of how current moves in real life, which is through electrons. We're just talking about how positive current actually flows. Okay, so that is just a keyword that I'm going to define, which is that current is defined as the rate of flow of charge. And keyword is positive charge. This actually lets us write an equation for current, which is that current is defined with I being equal to Q over T, where Q is the charge, which is measured in units of coulombs, named after a scientist. I is the current measured in units of amperes. and t is the time which we try to measure in seconds. Okay, so this is the equation that relates current to charge and time, but that's really just based on the definition of what current actually is. It's the rate of flow of positive charge, which means that it's the flow of some amount of charge in some particular amount of time. Okay, that's what we define current as. Another point about this is that remember that we can really only let the current flow if there is a closed loop. We call this closed loop a circuit. Okay, so we don't really even use the word circuit in science. A circuit can also be used in normal English. The most common place where I've seen it being used in normal English is just when you're talking about the Formula One races. So the Formula One races, for example, those are cars driving in a closed circuit. So they call it a circuit because it's a closed loop, right? So in the context of physics, a circuit is a closed loop of wire, which can transmit a charge from one area to another. Okay. Now, another point as well is you should notice that in order for the current to flow from the positive terminal, which we can call the anode, to the negative terminal, which we can call the cathode, okay, in order for the electricity to flow from the positive end to the negative end, there needs to be something that's driving that electricity in the first place, okay? And this is where the concept of voltage comes in. Now, some of you might have heard voltage being called as potential difference. I use them interchangeably. There's not really much difference between them, okay? So you can use the word voltage. You can use the word potential difference as well. Typically, when we're talking about sources of voltage, we use the word EMF instead, which stands for electromotive force. But in this case, I'm just going to simplify the language that we're using for a moment. I'm just going to try and call it voltage for the time being, okay? But just be aware that if you read up in a higher science textbook, EMF is referring to what's producing the voltage, and voltage is really referring to what device is taking up that electrical energy, okay? Now, anyways, in order to drive this charge out of the battery needs to have enough potential difference across its ends. The potential difference is another word for voltage. So voltage, you can define this as the energy transferred per unit charge. So this would have its own equation of voltage being equal to the work done or the energy transferred, because remember they're both equivalent, divided by the charge, which is in coulombs. So again, this is just the voltage, which is measured unsurprisingly in units of volts, but it's actually named after a scientist named Voltaire. And then E is the energy, which if you recall is just measured in joules. Okay, so what that means is if you have a battery that's got 6 volts, then that's basically telling you that that battery will give you 6 joules of energy for every single unit of charge that passes out of that battery. And if that battery rating also has a current attached to it, like maybe 5 amps or 5 amperes, then that means that that battery is transferring out 5 coulombs of charge in one particular second. Okay, so that's how you can interpret what current and voltage is. Now, a very common question is about which one of these is more dangerous, whether current is more dangerous or whether voltage is more dangerous, okay? You will see some people say that current is more dangerous and you will see some people say that voltage is more dangerous. In reality, it's really both of them together that need to be high enough in order for it to be dangerous to someone, okay? Because remember, voltage is about how much energy is transferred, whereas current is about how much charge is transferred in a particular amount of time, okay? So it's really only if both of them are big together that the energy transferred will be significant enough to cause some kind of heating damage. All right. So typically speaking, if you have a really high current but a really low voltage, it's not going to do anything. But if you have a really high voltage and a really low current, again, it's not really going to do anything. Okay. In fact, if you know what a Van de Graaff generator is, right, that's one of those devices where you have like this rubber kind of base and then a metal dome structure here. So we call this a Van de Graaff generator. And if you put your hand onto it, what it does is it actually makes your hair all spiky and stand up, right? That's because of static electricity, which we'll cover in a moment. But the main idea, the reason why I'm mentioning this is because in a Van de Graaff generator, if you touch that, you don't really get a current shock from it. You could get like a mild current shock from it, but the voltage from a Monte Graph generator is incredibly high. And despite that, you don't see anyone getting electrocuted from it, right? So the main point here is to understand that when you're dealing with current and voltage, it is both of them together that have to be high in order for it to be dangerous, okay? With that said, it's still bad practice to not try using some kind of insulator when you're dealing with a live circuit or anything like that. You always have to make sure that the circuit's either switched off, and that you are also wearing some kind of insulating apparatus towards the circuit so you don't get electrocuted, right? But these are the two key terms you need to just be aware of, okay? And you have to make sure that you understand them as well. So just to give you another analogy to drive the point home, okay? You can think of the current as the number of electrons per second, okay? You can think of that with the analogy. It could be a post office, that's the battery building, okay? Which is the post office. And out of this battery, there's a bunch of postmen walking out, okay? The number of postmen leaving the building corresponds to the current. But the package, the weight of the package that each postman carries corresponds to the voltage, okay? The rule is that whenever the postmen are leaving this particular battery here, okay, they have to deliver the package to the homes, and only then are they allowed to return to work, right? So again, if you've got a lot of postmen with small packages, that's the same as a high current but a low voltage. If you've got this one postman with a huge package, right, then that would be instead a high voltage but a low current, okay? So another analogy that I can think of for it is that you can think of having a low current but a high voltage is like giving someone a really strong singular punch, okay? But having a high current but a low voltage is like giving someone a lot of really small taps, I guess, right? Like, so just in, I don't know, in 1 second you give them like 10 taps with your hand, right? That would be a high current and a low voltage, okay? So just make sure you keep that in mind, because this fundamental understanding is important to understand how circuits actually work, okay? Now, one more thing as well is with these circuits over here, okay? We don't always want to draw circuits as this battery and then a bulb with these wires in a realistic kind of depiction here. So we will want to simplify them using circuit symbols. Now, circuit symbols look something like this. There are a bunch of basic ones that you need to know about, and I'll just go through them in order. So we can start off with the simple circuit symbol, which is just a line that's used to represent a wire. And this is the part of the circuit that actually conducts the electrical charge. And then we can have a cell. The long end of the cell is the positive end, and the smaller end is the negative end. This is the notation that we use, okay? So the long part of it represents the positive, and the smaller part of it represents the negative. The way that I remember it is that the smaller sign is like a inverted negative symbol. The longer sign is like two of these sticks of a positive symbol broken up. So you're breaking them up into these two kinds of negatives, and then you join them up to get a longer stick. That's how I remember it. Okay, there's not really a rhyme or reason for why this is the case. It just is how we've invented the convention. So this is called a cell, which provides voltage to the circuit. Okay, so this actually provides the voltage source to the circuit. You can call the voltage source the EMF as well, which again is the electromotive force. And then we have, if we stack these cells together, we can call it a battery. Now, if you have many cells stacked together and you don't want to draw all of them, you just draw a dotted line here, and then you end it like that. So this could be used to represent a battery. And the reason why we would do this is to try and increase the voltage. So, for example, if one cell gives me 1 volt, then 10 of those cells stacked up onto each other in this kind of direction in series would be 10 volts that it would give me. Okay, so this increases additively like that. Now, that's for a wire cell and a battery. The other symbol you should know about is just what is the bulb that we drew up there. But even before that, let's draw the bulb down here. You should also know about what a switch is. So a switch can either be open or a switch can be closed. If a switch is closed, then the circuit is complete and it will run. So a closed circuit allows the charge to flow in the loop. Okay, whereas the open circuit prevents the circuit from even working. Okay. With that said, that doesn't necessarily mean that just because the switch is open or that the circuit is switched off means that it's safe to prod around in there. The most dangerous thing in the circuit is the EMF source. So even if a switch is on, you still have to make sure that the EMF source is dealt with and the EMF source is disconnected from the circuit. If the EMF source, if there's a wire from the EMF source that's still something that you could touch, if a part of your body is attached towards a lower potential difference like the earth, then that could cause electrocution. So we will go into that in a bit more detail, but just remember, okay, in terms of like the practical aspect of it, having an open switch doesn't suddenly mean that the circuit is now safe. Okay, you have to consider what's happening with the EMF source. So just be mindful of it, and that's also again the reason why it is just always safe practice, because you don't know how circuits have been wired up inside walls and so on. It's always safe practice to wear some kind of plastic insulator if you're ever dealing with any of this. Okay, now for a bulb, we can use this symbol here. You can also use this symbol here. They are pretty much equivalent. There's also this symbol here, where you have like these 3 lines which represent a filament. So you can use any one of these. I tend to just use this cross here to represent the bulb. Okay, and then you can also have a resistor. So now here's a part where I need to talk about a law before I can explain what a resistor is. Although, spoiler alert, it's just as the name says, it's a resistor, so you can probably guess what it does. But let me give you the formal like rundown of where this component actually comes from, like what's the premise of it. Okay, now a long time ago there was a scientist named, I believe, Ohm, and he was investigating circuits. He invented a law that's called Ohm's law, which is really important to this day, and we tend to use it for simple circuits. There are some cases where the law doesn't work, so I'm just going to write it down right here. Okay, so again, this is relevant towards resistors, right? Now, Ohm's law states the following. It states that the voltage across a conductor is directly proportional to the current flowing across it. In case you're wondering what that means, basically what that means is if you double the voltage in a wire, then you're also going to double the current. If you're doubling the current in a wire, then you're also going to double the voltage. If you halve the voltage, then the current will also be halved. That's what this law is saying. But this law doesn't work under every condition. It only works if the temperature is kept constant. So again, so long as the temperature remains constant. That's the key criteria needed for Ohm's law. So for this, we can derive the following expression. And we can write this equation here as a constant from the fact that these two quantities are directly proportional. We don't write this constant proportionality as K though, we instead write it as the most common symbol of R. And we define R as the resistance. So R is just defined as the ratio of the voltage to the current. Okay, typically what it basically means is it tells you how much voltage you need to put into a device in order to flow a charge through it. Okay, you can kind of think of it as how much energy you need to spend to actually push something through a device. Okay, so that's what the resistance tells you. So if the resistance is really high, then you've got to spend a lot of energy to actually send a current through a device. Okay, now that means that current can theoretically flow through anything at all, but the energy supply needs to be strong enough, needs to be high enough, right? So basically, something that's an insulator like plastic would be having a really high resistance. That doesn't mean that plastic makes you safe from a lightning strike. It just more so means that, you know, plastic requires way more energy as a shield to be bypassed. It doesn't mean that it makes you perfectly safe, right? What would make you safe is standing underneath a building where the building is earthed by some kind of lightning rod. That's like the safest thing that I can think of. But again, being at a high altitude and having like a rubber hat on is not gonna like protect you, because again, it's to do with just whether that resistance of the material can withstand that amount of energy that's going to send the current through you, right? So like another really good example of this is if you look at wood, for example. Wood is also an insulator because it has a high resistance, but that doesn't mean trees are, immune to lightning strikes. They still do get struck by lightning. So again, it's to do with the amount of voltage that's in the supply, right? So if you look at a conductor, that's like the inverse example. So in the case of a conductor like a metal, like copper, gold, silver, etc., right? They can all transmit electrons really easily because of their metallic bonding. And because they can transmit electrons really easily, what that means is that they have a really low resistance, right? And it's for that reason that, metals are called conductors. It's because they have low resistance. So resistance as a concept is a really useful fact, right? Because you can use it to classify whether something will slow down a current or whether something will speed up a current, in a sense, okay? The reason why we might want to use it for an electrical circuit is because let's look at the example of a bulb, okay? Now, firstly, remember what the resistor is going to do is the resistor is just going to provide resistance to the circuit. Now, if I have a bulb in a circuit and that bulb is attached to a battery that's giving it a current that's way too high, that current is going to zip through the bulb and it's probably going to make the bulb shatter and burst, okay? Which is not what I want. I want to use a bulb to actually just get light energy and light up my room. So the way to protect our devices and make sure that the current flowing through them is minimal, that's the job of a resistor. So typically every single device that we're using uses a resistor because that will slow down and lower down the amount of current that's passing through them to make them safe to be used, right? So that's how you can think of resistors in that context. So a bulb is just converting that electrical energy into light energy. That's the main function of it. But of course, in a filament bulb, in reality, what's actually happening is majority of the energy instead becomes heat energy instead, right? Now, the reason why that happens, you need to understand how a bulb actually works, okay? So inside a bulb, we've got this very thin filament of wire, okay? And this bulb, like this wire here, which is usually made up of tungsten, is actually sealed in this glass kind of ampule here, okay, which is filled with noble gases of like argon or something that's unreactive like nitrogen. That's cheaper to get because like 70% of our air is made up of nitrogen, I think. See, not 70%, I think 79%. It was some amount like that. I believe it was 79. Either way, we have a big chunk of our atmosphere that's made up of nitrogen. So nitrogen is a cheaper alternative to use than a noble gas like argon because those are rare to get. But the point is, when the current is now flowing through this filament, okay, you have insane amount of current flowing through this really tiny wire. That's like squeezing a lot of particles into a tiny bridge, which is going to cause a lot of friction. And that crazy amount of friction causes more heating. And the more heating there is, well, that's what's going to actually cause this temperature of this filament to rise up and therefore produce light and heat energy. That's basically how a filament bulb works, okay? Nowadays, we don't use filament bulbs as much. We use a better device instead, which I'll come on to in a second. But otherwise, this is how a filament bulb typically works, okay? Now, apart from a resistor, there are different variations of resistors as well. For example, you can have a device that's called a thermistor, which we draw like this. Okay. I would probably argue that thermistors are one of the most useful devices apart from LDRs. They tend to be very helpful because of the name itself, right? Thermistor is a combination between resistor and thermal, which is referring to thermal energy, which is heat energy, which is to do with temperature, right? So a thermistor is a resistor whose resistance depends on the temperature, right? So the resistance of it depends on the temperature. The way that they work is really fascinating. I'm not going to go into it into that much detail right now, but they are made up of materials that are called semiconductors. A semiconductor would be something like silicon and carbon, but most thermistors are made up of a material of silicon that's doped with something else. Doping just means you're adding some amount of impurities to something else, like phosphorus, or maybe even like sulfur or nitrogen. So it varies depending on the type of thermistor you're trying to make. But anyways, right, you've got two types of thermistors. You've got something that's called an NTC and a PTC. An NTC stands for negative temperature coefficient, and a PTC stands for positive temperature coefficient. An NTC thermistor is a thermistor where if you increase the temperature around the thermistor, then the resistance of it will decrease. And a PTC is the other way around. If you increase the temperature, then the resistance will increase instead. Okay, so just to note down, the most important one that we use is called an NTC, which stands for negative temperature coefficient thermistor. And this is the type of thermistor where when you increase the temperature, that will lead to a decrease in the resistance of the thermistor. Okay, and the reason why this is so helpful is because this is the component that you use when you're trying to use any kind of machine that is trying to control temperature. So whether it's a fridge, or whether it is a fire alarm detection circuit, or whether it is an oven, or whether it is the inside of your phone checking whether it needs to switch the fans on to cool the phone down, or the computers, that's all controlled by the thermistor, essentially, right? So thermistors can be used to monitor temperature. Okay, that's the point of how a thermistor works. Now, similarly, we've got another component that's called an LDR. An LDR that stands for light dependent resistor. And in a light dependent resistor, it basically looks like this. You've got this rectangle here, and you have two arrows over here, these cute little arrows, and those are just meant to represent these rays of light that are hitting the resistor. Okay, so on this LDR, the way that it works is exactly the same as a thermistor, but instead of temperature, it's now controlled by light intensity instead. And light intensity is just a fancy word for the brightness. Okay, so if it's very bright outside, then in the case of a negative coefficient LDR, if it's very bright outside, then the resistance is going to be lower. And if it's very dark outside, then the resistance is going to be higher. Okay, so again, for this guy, the resistance depends on the intensity, which is the brightness. Right? Now, that means that this is ideal to be used in automatic lighting systems, right? So if you want the street lights to turn on automatically when the lights in the sky are dark, right, then you could use an LDR, for example. So it can be used in automatic lighting of a house, it could be used in automatic lighting of some kind of street light and so on, okay? But it's not always the case that we want to use an LDR and a thermistor that's dependent on the temperature and the light. Sometimes we want to control what the resistance should actually be. Okay, the problem with the resistor up there is that this is really a fixed resistor. This symbol here is for a fixed resistor that provides a fixed amount of resistance, maybe like 100 units or something. Okay, that actually brings me to this one more thing before I forget it, which is that the resistance is measured in these units. That is called ohms. We use this symbol for it. This is the Greek letter omega. It's a capital letter omega in Greek, and we use it in physics as short for ohms. So the unit for resistance is ohms. Okay, but as I was saying, right, sometimes we will want to control how much resistance a device is actually receiving. A really good example of this could be the volume, right? If you are trying to control what's the volume of your phone, for example, right, that would basically be you that's changing the resistance to control how much current is flowing into a device, right? Because if you increase the resistance manually, that would decrease the current, which would make the volume quieter. But if you are decreasing the resistance, then that increases the current, which is going to increase the volume. Okay, so that's an example of just one of many of a device where you would want to change what the resistance is yourself. Okay, we can't use a fixed resistor for that, so we instead use another type of resistor symbol that is called a variable resistor, which is the same symbol here, but we just have a line going through it with an arrow like this. You can also draw it this way too, like this if you want. Doesn't really matter. I'm just going to draw it like this for now. Okay, but this is a variable resistor. Sometimes people call these rheostats. Sometimes people even call them potentiometers. Those are just fancy words for variable resistor. Okay, but a variable resistor is a resistor whose resistance we can control. So it's a resistor that we can control the resistance of. It doesn't mean that the resistance randomly changes. It just means that we have control over it. It's like a volume slider button. Okay, so again, a variable resistor might be one of, I would, yeah, it's probably up there in the list of really useful circuit devices because you can use this to make a lot of systems dynamic. Okay, so again, the processing power of your CPU, like the darkness of the lighting in your rooms when you're controlling that, that slider. Like some fancy switches have this where it's like it's not as a switch, it's like a slider that controls how bright it is. And you can see this on the phone, for example, right? That brightness, the volume as well, the temperature of how hot an oven should be, for example, right? These are all controlled by a variable resistor. Okay, so if you're ever seeing something where you have like a scale to control it, most likely what's happened is an electrical engineer has set up this device for you in such a way that you can just look at the front part of it, which looks really neat, but the back part of it looked, like really messy, involving a variable resistor. Okay, but this right here is the device that's allowing that kind of, that kind of science to happen. Okay, now apart from a variable resistor, there was one more device that I wanted to talk about, which contrasts to the filament lamp up here. Okay, before I can talk about that, I need to talk about something that's called a diode, which has this symbol here. Okay, so here's where things get a little bit confusing, but let me try to explain this to you. So the thing about current is that current is just defined as the movement of charge, right? As long as charge is moving, then there will be transfer of energy. It doesn't necessarily mean that the electrons have to always go into a bulb. It could also be that the electrons are leaving from that bulb. As long as there's a transfer of charge, there will still be transfer of energy. Okay, that's the key point I want you to take away. And the reason why I'm mentioning this is because current really comes in two types. We have one type that's called DC, which is a direct current. And we have another type that is called AC, which is an alternating current. You might have heard of the band called AC/DC. AC/DC actually gets their name from this. I think the story was that they were sitting in a garage and they saw like an old garage device which had the word AC/DC on it because it's a machine. So they took the name for their band as AC/DC, right? But that's where it actually comes from. So AC stands for alternating current and DC stands for direct current. So direct current is current that only travels forwards in one direction. The graph for it would look like this. If I drew the current over time, it would look like this. Alternating current, on the other hand, looks more like this, where it's traveling like a wave. It becomes positive 1 second and negative the next. In case you're wondering what that looks like, that would be more like a hacksaw, right? Where it's going left and then right and then left and then right, okay? So in the case of direct current, if you had a bulb, the bulb would always stay lit on when it's receiving direct current. But to alternating current, if the frequency is low enough, then you will see the bulb glimmer on and then glimmer off and then glimmer on again and then glimmer off. Okay, the negative currents over there doesn't mean that the bulb isn't on. The bulb will only be doesn't mean that the bulb's off, sorry, right? The bulb will always be on for these points here as long as there's a movement of charge, but they will be off for these points here where there's no current, there's no transfer of charge. Okay, and again, the way that you can think of this energy transfer is again like a hacksaw, where you're holding both ends of a saw. You move the saw this way. No matter what way you go, you're still doing work done to it. You're still like giving it this electrical energy. Okay, in the case of direct current, it's just always moving in one direction. Like I guess you could think of it like a chainsaw, I suppose, right? But in the case of alternating current, it's more like this kind of hacksaw that you have to manually move left and right. Now, the reason why we have two kinds of currents, okay, is because if you have a device like a battery, that will always provide a steady amount of direct current, all right? But in the society that we live in, we use power plants which generate current as alternating current instead, Okay, so majority of the power plants that we rely upon, like wind power plants, nuclear power plants, um, thermal power plants, etc., they all actually produce alternating current, which is oscillating left and right. Okay, so they don't convert the alternating current to direct current. They just leave it as alternating current, and that alternating current gets shipped all the way towards our houses, and our machines will convert that alternating current into direct current to be used more effectively. Okay, because again, for a bulb, we wouldn't want it to glimmer on and then off and then on and off. We want it to just be glimmering constantly. So usually many of our devices will have a component in them that will convert the alternating current into a direct current. And again, the reason why we have two kinds is because power plants produce alternating current, whereas direct current is produced by things like batteries, but we don't always use batteries all the time. Okay. Not every power plant produces alternating current. Some produces like solar power plants, for example, they produce direct current. But again, we tend to convert it to alternating current for other reasons that you'll see about, like that you learn about later on. Okay. Anyways, so this brings us back to the diode. The reason why I went that long tangent is because the function of a diode is to allow the current to only flow in one direction. So it only allows the current to flow in one direction, whether it's left or right or whatever. In this case, for this particular diode that I've drawn, it only allows the current to go to the left. So what that means is, if I have a diode and I attach it to a battery like this, okay? Now remember, in physics, current is defined as a positive flow of charge, right? So I've got the positive terminal here and the negative terminal here. If I have a diode like this circuit is not going to work in my notation, okay? But if I have a circuit like this, then this circuit is going to work. So this is a circuit where the diode will actually function to allow current to pass through it. And this is a circuit where the current's trying to go this way, but it's blocked by the diode, so it's not going to work. Okay, that's the job of a diode, right? We can actually go a bit further with diodes as well to make another kind of device that's called an LED. You might have heard about LED lights before. So LED stands for light emitting diode. Okay, so it's the same exact symbol, but it's got lines popping out of it. So an LED has the same exact function as a diode. The only difference is that when current passes through it successfully, it will release light energy, right? So this produces light when current passes through it. Okay. The main difference is that if you compare a filament bulb to an LED, a filament bulb produces a lot of waste energy, like 99% of the energy is wasted as heat energy instead. But an LED will instead produce, I think it's like 99% of the energy just becomes light energy. It's actually very efficient, right? So my point anyways is LEDs are way more efficient than filament bulbs are, right? So something to just consider if you're ever buying one. I think nowadays filament bulbs are quite rare to even buy. We use another kind of bulb instead. It's called an incandescent light bulb, I believe. But even those are not as efficient as LEDs. What you see on the market is that LEDs are very expensive. But the reason why they are very expensive is because it is a bit of an investment in the sense of, firstly, manufacturing them is quite complicated compared to an incandescent light bulb. But also, secondly, if you do buy them, you will save money on your electricity bills, right? So remember, when you are buying a device, also consider, like what is the actual lifespan of the device and what is the actual energy bill usage of the device, So those are numbers to look at if you're ever going to buy some kind of device, okay? But in these two circuits I've drawn over here, the one on the left, the LED will not glow, but the one on the right, the LED will glow. Okay, a lot of electricians will also use LEDs to figure out whether a device is working or not. They will use it to troubleshoot a device. Usually, every device that you use, whether it's a monitor or a TV or a washing machine or whatever, they will always have a tiny light on them that shows whether it's receiving current or not. That is what we call the LED. That's the first LED in the device, which signals to the electrician as to whether that device is receiving current in the first place or not. So it's something that the technician can use to probe and troubleshoot whether the device is working. All right, now one more device as well that I want to mention is the fuse. We don't tend to use these as much anymore, but by law in certain places, fuses have to be included in sockets. Otherwise, companies can be reprimanded for it. They're not as helpful anymore, and I'll explain why, I suppose. But this over here is called a fuse. Okay, this line over here represents the tiny wire that's inside the fuse. The way that the fuse works is if for some reason the current suddenly increases in size out of nowhere and is headed your way, okay, that current is going to potentially damage or maybe spoil the machine, or and in the process damage you as a result. Okay, to prevent that from happening, we have a device that's called a fuse. A fuse is a very small section of a circuit that is made up of a different wire. Usually we use tungsten again, but that wire is purposefully having a different metal with a lower melting point as opposed to the rest of the circuit, so that if the current becomes too high, then that wire will melt. And once the wire melts, it's going to disconnect. And once it disconnects, the circuit will be broken, and once the circuit breaks, there's no way for the current to actually harm you, or you'd get just a singular shock, if anything, right? So this is just used as a safety measure. So it protects, or rather, let's just say it disconnects the circuit. When the current is too high. Yes, remember I stands for the current in symbols for physics. Yeah. So it disconnects the circuit when the current is too high, and back then, whenever there was some kind of current, some kind of sudden increase in voltage or current, that would always lead to the fuses getting blown. So you would have to actually replace the fuses as a result, right? So a lot of sockets now have fuses in them because that's like a legal requirement. But in reality, fuses are, I would say, not as helpful anymore because nowadays, if there's ever a sudden influx of current into a building, there's another device that deals with it instead, and that's called a circuit breaker. A circuit breaker is a better version of a fuse, in my opinion, because unlike a fuse, a circuit breaker doesn't need to be replaced. So a circuit breaker is just a singular switch. You can decide to switch it on and off, and it automatically switches the circuit off without needing a replacement. Because in a fuse, you always need to replace it, because if the wire breaks, it just breaks. You've got to replace it with another fuse. But in a circuit breaker, that's a handier way of like switching off circuits. I can't go into it in much detail for the moment because we haven't gone through the basics of magnetism yet. But once we go into that section, I'll explain a bit more about how circuit breakers actually work. All right, so that over there is a fuse. Now, apart from a fuse, you should also be knowing about the basic ways to measure the current and the voltage of a circuit, for which we use these devices here. This A over here stands for an ammeter, the am referring to amperes, and the meter for meter. And V over here refers to a voltmeter, okay, where V is referring to the voltage and we're measuring that as a meter. Okay, so we've got an ammeter which measures the current, and we have a voltmeter which measures the voltage. So what I'm going to do for you is I'm just going to draw an example of a typical circuit that you could use to measure what is the current and the voltage of some kind of component. Okay, so let's say that in this case we were trying to measure what is the voltage and the current of a bulb, and we are trying to find out what the voltage and the current is for different levels of current. Okay, so we'll have our battery supply here, and next to this battery supply we will have our switch, which we'll just keep closed, and next to this switch we will keep our bulb over here. We need to be measuring the current that's passing through this bulb, so we can just place an ammeter right here, because this ammeter will be measuring the actual current flowing through it. And we need to also measure what is the potential difference before the bulb and after the bulb, right? Because we want to know how much energy this bulb is using up before and after. So that is going to correspond to having a voltmeter attached in parallel like this, right? So we say that this voltmeter here is in parallel and this ammeter here is in series, right? So the ammeter is connected in series because it's in the same singular line, but in parallel it just means that it's in a branched off line like this. final thing that we can do is we can have a variable resistor here, so we can decide how much current we want flowing into this bulb over here. Okay. Alternatively, you could also just be using stronger and weaker batteries with different voltages. But what we can do is this over here will then display different numbers of voltage for us and different numbers of current for us based on how much we are varying the resistance of this variable resistor here. Okay. The graph for a filament bulb tends to look like this if we plotted them onto a graph, right? You'd have the voltage here, and let me draw the current here instead, and the voltage here. It tends to look like this. Yeah, so something along these lines here, right? So that's what the bulb looks like for a filament bulb, and as that's what the current looks like for a filament bulb. And as you can see, one key feature about it is just the fact that it's very difficult for the current to increase. The current tends to level off. Okay, and the reason why that happens is because in a filament bulb, the metal's getting really hot. When the metal gets really hot, it's going to cause a higher resistance because the atoms are going to start to vibrate a lot more, right? So remember, in metallic bonding, you've got the metal cations. Those cations are going to start vibrating a lot more. And when they do vibrate a lot more, they're going to collide with a lot of the electrons, which is causing friction, which causes more resistance, which prevents them from increasing, right? So the hotter the bulb or the hotter the component, typically speaking, the resistance tends to increase. Okay, so that's the case for this bulb over here, right? In the same way, you can repeat this. Rather than drawing the bulb, you can also repeat this for a wire, you can also repeat this for a resistor, and you can also repeat this for a diode, right? And these are the kinds of graphs you would get. So you'd see for the bulb, it was the red graph up there, but for the wire and the resistor, it's just a straight line of voltage against current. And for the diode, if I do voltage here and current here, if the voltage is negative, we're not going to see any current passing through it. But the moment the voltage starts flowing in the right direction, then we have current that passes through it. So this is how it looks like for a diode or an LED. Okay, one more small thing as well is just that talking about series and parallel, you should just be aware about some of the differences between parallel circuits and series circuits, right? So if I have an example of a series circuit here, I could have a battery with two resistors in series, like this, okay? Now, one thing to note is that the amount of postmen, right, or electrons or charges that are leaving this end must always be equal to the amount entering. You cannot just have a postman that magically disappears. The postmen, the electrons, right, because I'm using the postman analogy, right? So the electrons will always remain constant. If one electron pops out here, it's always going to be one electron that moves, like this. If two electrons pop out, then two electrons must enter. Okay, so that is to say, across any point in a series circuit, the current is the exact same. However, the energy supplied, which is the packets given by the postman, needs to be evenly distributed. If both of these are identical resistors, then if this had, let's say, 6 volts, this would be receiving 3 of those, and this would be receiving another 3 of those. So the voltage is shared. Okay. Additionally, as well, you can also show that the total resistance, RT, of a series circuit is given by this R1 plus R2 plus so on. So if you have a bunch of resistors lined up, you just add them up like this, okay? In parallel, if you have a battery like this, and then a resistor here, and here, and so on, okay? What's going to happen now is, if you've got two postmen walking out, they have to split up at this node over here. One of them needs to go this way and another one needs to go this way. The packages don't split up, but the postmen themselves that are carrying that package do split up, right? So that is to say, in the actual like scientific words, when a unit of charge passes out of this battery, the charge, right, one unit of charge needs to move to the right, the other unit of charge needs to move to the bottom. Both those units of charge are carrying the same amount of energy, right? So if this was 6 volts, this also receives 6 volts and this also receives 6 volts. But if this was, let's say, 10 amps, then this would be 5 amps and this would also be 5 amps, right? So in a parallel circuit, the current is instead shared, but the voltage is the same, okay? There's another equation for parallel circuits as well, which looks like this. That 1 over RT, which is the resistance of the total like circuit, is equal to 1 over R1 plus 1 over R2 and so on. Right? And you can derive this by using Ohm's law and the fact of what I've explained over here, that the current needs to be the same, but the voltage needs to be shared and vice versa for the parallel circuit. Okay, so you can derive these by using Ohm's law and so on. Right. Other point as well is just that a series circuit tends to be cheaper to make because it requires a single strand of wire, but a parallel circuit needs a lot more nodes and connections, so that tends to be more like expensive to make. But with that said, a parallel circuit tends to be better to use because in a series circuit, if one component breaks, then all of the rest of the components don't work anymore. Because if one component breaks, it's probably because the wire has been cut off. So if a wire cuts off here, then this component is not going to work anymore. So if you have Christmas lights where one of those lights break, the rest of the lights are not going to work anymore. Okay, that's like an example of a series circuit not being that effective. But in a parallel circuit, if one of those resistors or bulbs breaks, then the rest of the circuit will still work. Okay, and that's the advantage of a parallel circuit as opposed to a series circuit, right? So there's a time and a place for when you might want to use a parallel circuit compared to a series circuit instead. Now, apart from that, there's a few more things that I just want to cover really briefly, and we're just going to go back to the practical world. Okay, now this links towards what we just discussed in the first lecture, which was to do with electrical energy and the other kinds of energies as well, right? Now remember that current is defined as the charge per unit time, and voltage is defined as the work done or the energy transferred in some amount of charge. If you take both of these quantities and you multiply them together for VI, that actually gives you E over Q multiplied with Q over T. The Q's end up cancelling and you end up with just the energy transfer per unit time. That is to say, the power, which is the electrical power, is the same as the voltage times the current. So if you wanted to figure out what was the electrical power in watts, you just multiply the voltage and the current. And if you wanted to get the electrical energy, that would just be the voltage times the current times the time. So these are two like handy equations to just keep in mind, right? If you're ever investigating what's the power output of something or what's the energy output of something, just multiply voltage, current, and time for energy, okay? Now, the other thing that we were going to talk about just practically are the different kinds of wires that you would see if you're dealing with any kind of circuit, okay? So this actually corresponds to the plugs on a socket. Okay, we tend to have like one here and then two down here, okay? One of these plugs is going to be called the earth wire, or the earth socket, I suppose. The other would be called the live, and the remaining one would be called the neutral. Okay, the live wire is the socket that is, or it's the plug that's actually providing that dangerous voltage. Okay, so this actually provides the higher voltage. This over here would be having 0 voltage. And this over here will also be having 0 voltage, but these two have different functions. The live wire provides the high voltage. The neutral wire carries back the current, because remember, it needs to be in a closed loop. So one comes out, one goes in. So this carries back that current from the area of high voltage to the area of that low voltage, right? So current always needs to flow from a region of that high voltage to a low voltage, right? Just like how water needs to flow from a high spot to a low spot. So water always flows down as per gravity, right? That's water's way of traveling from a high energy level to low energy level. In the same way, for electrical energy, that needs to travel from a high energy region, which is high voltage, to 0 voltage. Okay, so current will always try to pick the path of least resistance to do that, right? The problem here comes in the fact that if you had a direct connection from this live wire to yourself, and if your hand was maybe a little bit like wet, right, which it decreases the resistance, right, that would cause you to become electrocuted. Okay, the problem with that is that even if you are not using a device, like even if you're not having your hand there directly, maybe it's plugged into a device, for example, right, and that's electrocuting you. Okay, the main problem is the device is going to be harmed, and then you would be harmed as a result, and we would want to prevent that from happening. the way that we do prevent that from happening is by using an earth wire over here. Okay, the way that the earth wire works is you have an extra wire from the circuit that connects directly towards the earth. Okay, so we call this process grounding or earthing. And this is basically the process of connecting the wire to the earth to discharge any excess current. Okay, and again, remember how current works. Current always tries to pick the path of least resistance, right? It picks the laziest pathway for it to travel, basically. Okay, so what that means is if you've got current that has the choice of either traveling through you or traveling through this easy, this easy path of a wire here, it's going to pick the wire. Okay, so that's the reason why the earth wire exists. If the system is ever able to detect that the machine is receiving an absurdly high amount of current, it will activate the earth wire, which will discharge that current towards the ground instead, right? So that is the function of the earth wire. So you always want to make sure that your devices are earthed properly. Some sockets don't have an earth wire included. For those sockets, they would, by law at least, be required to have a fuse in them. Okay, but typically speaking, even if they do have an earth wire, they tend to need to have that that fuse in them because that's just a legal requirement, I suppose, right? But that is one of the main points here. So just keep that in mind, that an earth wire, which is usually having this green and yellow stripes on it, that needs to discharge the excess current into the ground. A live wire, that tends to be brown or red, and that's providing that higher voltage. In some countries, it's 230. In some countries, it's 115. For example, I believe in America, it's 115. But I believe in European countries, it's 230. And then the neutral wire just has that 0 voltage to bring the current back into the battery to actually complete the circuit, because the circuit won't work unless this is done. Okay. Just the last point that I want to mention is just to give you an overview of how this looks like, where we're actually getting that current and electricity from, right? So I briefly alluded to the PowerPoints that we had, the power plants, I suppose. Hold on. Okay, so we've got many power plants that will produce electricity for us, or produce electrical energy for us, I suppose, right? And they harness different kinds of energies out there: solar energy, wind energy, and so on. The primary one that countries use is thermal energy for the time being. But what these power plants do is once they produce that energy is sent through a device that's called a transformer. And then it's sent through cables, through which it is sent through another transformer back to our houses. Okay, so this is like the pathway of how energy is transferred from the power plants towards our houses. And the cables here tend to be very complex. They're a long kind of grid of cables that stretch throughout the country. Okay, so what you should know is that when the power plants produce electricity, they are producing power at a really high voltage. Okay, which is fine. Sorry, I've got it mixed up. They produce power at a really high current and a low amount of voltage, okay? Which again is still fine, because remember from the equation, power depends on voltage times current. So it doesn't really matter if you increase or decrease one, it's not going to do anything, okay? But the issue is that if you cause a high amount of current to flow through a wire for a very long time, as it was in the case of the filament bulb that we discussed about earlier, which was heating up, it's going to cause the cables here to heat up. The problem becomes the fact that this is going to waste a lot of electricity, a lot of energy, which is a lot of money. Okay, so what we do is, before the electricity has a chance to go into the cables, we use a transformer to change the voltage. So what this transformer does over here is it increases the voltage and decreases the current. And this is done to save energy by reducing the amount of electrical energy that's converted into heat. And then to make the current safe to use again, we will then have another transformer to inverse that effect. So this will now decrease the voltage and increase the current before it actually enters our household, right? So this is the typical kind of diagram of what it looks like for every country out there, right? You've got a problem that produces this current. The transformer is this nifty little device, which we'll go into how a transformer works later on once we're covering magnetic fields. But otherwise, this is basically what's happening there. Okay. Now, the last thing I just want to cover is the nature of electricity. We've talked about electricity that's dynamic in the sense of electricity that's moving, but that's not the only kind of quote unquote electricity that you could have. You could also have something that's called static electricity or static charge, right? That comes from when you have an accumulation of charges onto one particular area. Okay, so you can refer to this as static charge or static electricity. So again, this is basically the buildup of charge, right? There are two ways you can build up charge. You can even do this at home as well. The first way is something that's called charging by conduction or friction. The second way is called charging by induction. You might have heard of induction chargers. That's the second method here. Okay, but just to explain to you what's happening, in charging by conduction, what we have is we can have, let's say, some kind of woolen cloth, and we can have this rod over here, like a plastic rod. Both of these have to be insulated for it to work effectively. But essentially what we are doing is we take the rod and we rub it against the cloth, right? That causes friction between them. The friction actually strips away the electrons from one material to another. So if the cloth gained more electrons, then that would leave this rod here with a positive charge. Of course, if you wanted to get rid of the charge, you just need to earth it with a metal wire, right? Or if you're holding it with your hands and then you are standing on like metal ground, that would, again, it would earth the rod, right? But that's how you can charge by conduction. Charging by induction is when you're charging something without contact. So that is when you already have a charged object. You bring that close to another object. This object, which is neutral, right? The electrons of this object are going to be repelled and they'll move to this side here. And this side is going to lose those electrons because they've moved down here. So this side is going to appear as a whole now positive. And what we can then do is we can sneakily add a earthed wire here. From these electrons' perspectives, these electrons want to get away from the negative charge as much as possible, so they're actually going to go ahead and earth themselves. And that will lead to this rod that is this positive over here throughout, right? Especially once you remove the earthed connection. That's like an example of how charging by conduction works, as well as how charging by induction works, right? Both of these objects will also exhibit electric fields between them, right? I might not go into that much detail for just a moment, but I want you to just be aware of them for the next time that we do go through them. We will go through them in a lot more detail later on. Probably not anytime soon, but much later on, because it's a bit of a complicated topic. But just to give you a bit of a rundown of what electric fields are, you can think of an electric field as a model that we use to visualize how these rods will attract one another, whether they will repel, or whether they will attract, or whether they will, like, what kind of directions they will move in if they're going to attract, right? That's all visualized by electric fields, right? So we will investigate this much more later on, but just so you know, if you are ever drawing an electric field, there are two rules to follow. The first rule is that the lines don't intersect. And the second rule, very simply, is just that they go from positive to negative. So if I was drawing the electric field lines between these two objects, I would just have lines like this. And you can draw as many as you want, doesn't matter, but these two rules have to be obeyed. So using this principle, you could have all sorts of fields like this. And this might be reminding you of magnetic fields as well. So who knows? There might be some kind of link between them. But yeah, anyways, this is an example of what an electric field looks like, right? So this is another example. If I have an electron over here, you just have lines entering it like this. And if I have a proton over here, then I'd have lines leaving it like this. If I have a proton and a proton together, because of the first rule, which is that the lines cannot intersect, both of these have to be kind of moving upwards like this. Right? So these lines are not allowed to even like go here because they are not able to intersect each other. Right? What that means is, theoretically, if you were standing in this region over here, you wouldn't be feeling any electrical charge. Even if these two were really strongly charged, you wouldn't be feeling anything because the electric fields are not allowed to actually express themselves over here, right? So this example that I've just shown you is something that's actually called a Faraday cage. They've done this before to entertain people, where someone just stands inside a cage, and this cage has like a high voltage, but the person that's inside the cage has like, it's not harmed as long as they don't touch the cage, because again, you can see the electric fields are not allowed to go into that region. But that is a model that we have made up to understand better how the electric force actually works, right? So there's a bit of a disclaimer that I'll just mention with this, right? With all these circuits over here, I'm giving you the models of how the electrons are moving through the currents, okay? But these electric fields over here also play a huge part in how the energy is actually transferred, right? You can think of the energy being transferred in terms of electric fields, where you have the electric field that's being produced by this battery, and as that electric field passes into this component here, that actually causes an energy transfer. So you could also think of it like that as well, right? That's like the more like higher level or sophisticated way of thinking about it. But otherwise, the model that we're using, which is just, electrons passing through, it's realistic, it does happen, and it's also basically how the energy does pass through, right? But it is just in reality, just remember that it's not like the electron from here has to literally travel through here. It's more like you have this conveyor chain of electrons. One pushes the other, which pushes the other, which pushes the other, and that makes like a gradual river flow process, right? So that's like the more realistic view of what's actually going on here, right? But yeah, otherwise this covers the main basics of electricity, okay, for physics, which I think is a really interesting topic. And for next time, what we will do is we will just cover, I believe that would just be more about kinetic theory, which we'll discuss next time. And kinetic theory is a bit more on how do solids, liquids, and gases work. It's a bit more of how it relates towards temperature and so on. That's very interesting. And learning about that will give you a better understanding of what temperature actually even is in the first place, right? But that essentially covers it for electricity. If you enjoyed, let me know in the comments. If there's any criticism that you want to give me as well for feedback, just let me know in the comments as well. If you enjoyed as well and want to support this, then feel free to support me on Patreon. But otherwise, we'll pause here for the time being. See you then.